looks good.
Okay, so next talk by Viraj Pandya. Sorry if I am not spelling it properly.
No worries.
With the role of circumgalactic turbulence.
All right, thank you, Santi. Hi, everyone. My name is Viraj Pandya. I am a Hubble Fellow at Colombia, and I'm very excited to present a new model that I've been working on about the CGM galaxy connection with an emphasis on CGM energetics. This is work in collaboration with Drummond Fielding, Greg Bryan, Chris Carr, Rachel Somerville, as well as the FIRE team. So we know that the galaxy formation process is intimately connected to the global baryon cycle, so the way that gas accretes into halos and galaxies and turns into stars and gets blown back out via feedback. And so to understand galaxy formation, we really want to model not just the stars and the interstellar medium, but also the diffuse circumgalactic medium on larger scales. And what we would like, ultimately, are self-consistent and time-dependent models that let us translate beautiful illustrations like this one here into a set of equations that we can easily interpret. So what do we have already? Well, as you just heard from Claude Andre, we have many amazing hydro simulations that are able to predict in great detail the properties of the CGM, of the ISM, of stars, and the gas flow cycle. But of course, these are subject to subgrid physics uncertainties, and you still want simpler models to distill the key insights from these kinds of simulations. On the other hand, we also have many 1D models for the CGM, and these are very compelling also because they're able to describe the structure and properties of the CGM in both simulations, as well as observations of, say, the Milky Way CGM and around other galaxies quite successfully. However, these 1D CGM models generally don't simultaneously model the galaxy formation process, and they tend to be static in time. So you're modeling just the properties of the CGM at one single instant. And so I want to present this new complementary model that I've been developing for CGM galaxy coevolution with an emphasis on CGM energetics. And underlying this model are 8 coupled ordinary differential equations. And these ODEs give you the time evolution of 8 state variables that we've defined to keep track of various basic quantities for a single galaxy and its CGM as a function of time. So 6 of these state variables and their corresponding ODEs just tell you some very basic things that you might want to know. So you want to know what's the total amount of mass in the CGM versus time, what's the total amount of mass in the ISM, the total mass in long-lived stars, and then the metal masses of these 3 components. And this is old stuff. Classical semi-analytic models have been doing this for decades. But the new thing that we're adding are 2 ODEs that tell you the time evolution of the total CGM thermal energy and the total CGM turbulent kinetic energy. So each of these individual E dots and M dots on the right-hand side has a functional form associated with it, and I'll briefly just go through that in a second. But before I do that, I want to just show a schematic that shows what we envision for the structure of the CGM in this model. So let's imagine that we're at some instant along the trajectory of an individual halo. Our model tells us the values of the state variables. So you know, for example, the CGM mass, the CGM thermal energy, the CGM turbulent kinetic energy, the CGM metallicity, and so on and so forth. And so what we imagine is that, for example, the CGM mass is distributed with a density profile that goes as a power law. And since we know the value of the CGM mass at some time, we can just integrate over this profile radially to solve for the normalization, the density at our VIR. And then this power law slope, alpha n, is a free parameter of our model. So you can set it to whatever you want. We typically take alpha n to be -3/2 for a cooling flow solution. And then we also have a temperature profile, which is again also a power law. And so for simplicity, we typically take the power law slope for the temperature profile to be 0. So a flat temperature profile consistent with a cooling flow solution. But here's the thing that we can do differently and I think improve upon previous SAMs. Whereas previous SAMs assumed that the CGM temperature everywhere is the halo virial temperature, we instead know the value of the thermal energy. And so we can again just radially integrate to solve for the average CGM temperature via this T0 parameter out front. And the third component of our model is that we imagine that there are large-scale eddies, turbulent eddies, that are distributed with the distribution of sizes throughout the CGM. And this turbulence provides two things. It provides pressure support, and it provides a heating term via the dissipation of the turbulence. And so we have to specify two things about this turbulence in our model. The first thing is, what is the characteristic turbulent velocity? So we compute that in a very simple way globally for the whole CGM using this prescription down on the bottom right. And the second thing we have to talk about or define is the turnover time of the largest eddies in the CGM, because this is the longest time scale on which those largest eddies are going to cascade down to the smallest scales and then dissipate as heat and become thermal energy. And so this T-turb is equal to some free parameter, this size of the largest eddies, R-turb, divided by this characteristic turbulent velocity, V-turb. Now, we don't know what R-turb should be, in halos of different mass as a function of redshift and so on. So we have to make an assumption, and we assume for simplicity that this R-turb is proportional to the halo virial radius. So I've specified now the structure of the CGM in our model, and I want to just quickly fly through, how do we actually connect all the different M dots and E dots in our model? And this is basically a set of equations for the Baryon cycle. And so at any given instant, we're always going to have some cosmic accretion, and so we assume that the dark matter that accretes into a growing halo will bring with it some fraction of baryons, which may not always be the cosmic baryon fraction because of preventative feedback in dwarfs that we allow for. We assume that this accreting energy, that this accretion has a specific energy proportional to the halo virial temperature. And then we introduce a free parameter that we call F thermal accretion that splits this incoming energy into thermal versus kinetic forms. And then once we're in the CGM, we can compute a dissipation rate, this heating rate, very simply as just being the kinetic energy divided by the eddy turnover time for the largest eddies. And then we can easily compute also a radiative cooling rate. That's just doing a radial integral to get E dot cool. And then we compute the accretion rate into the ISM from the CGM in a relatively simple way, defining these effective cooling times and effective free fall times, taking into account your actual thermal energy that you have to radiate away, and the turbulent pressure support that will make the free fall times longer than just, say, RV over VV or V, or R max over V max and so on. And then we compute the star formation rate very simply. It's just being the ISM mass divided by a free parameter, the depletion time. And that then gives way to supernova feedback via wind. So again, as has been done for decades, we have this eta m parameter, the mass loading factor, the efficiency with which the supernova winds remove gas out of the ISM. But we have a new parameter that hasn't been used before in SAMS, and that is this energy loading factor. So what fraction of the supernova energy goes into the galactic wind, makes it out of the galaxy, into the CGM, where it can then have a heating effect and possibly suppress cooling, suppress future star formation, and so on and so forth. And we have a free parameter that partitions this wind energy into thermal versus kinetic fractions. And then I think the last and the coolest thing of the model, in my opinion, is it can happen in this model that cooling cannot keep up with heating. And when that happens, you basically have the CGM energy exceeding its own binding energy. So when that happens, we allow the CGM mass to basically vent and the energy to vent. So we have these halo outflows that are driven by CGM overpressurization. So you can take the difference between the CGM energy and the binding energy, use that to compute energy outflow rates, and then assume some specific energy for those halo outflows to go from E dot out to an M dot out of the halo. So this is the model. It's general as I've described it, and we're now working on a few initial or first applications of it. So I want to start by just highlighting this project that is being led by Chris Carr, who is an excellent grad student at Columbia. So what Chris is doing is he's forward modeling the stellar to halo mass relation while exploring the supernova wind parameter space of this model, specifically the mass loading factor and the energy loading factor that I talked about earlier. And we're doing this in the purely thermal limit of the model for simplicity, so no turbulence for this particular slide. And so what we're finding is that in this model, when you vary the mass loading factor as shown on the left panel, the stellar mass-halo mass relation is not very sensitive to changes in the mass loading factor. Instead, it's really varying the energy loading factor, or the specific energy of the supernova winds, equivalently, as shown on the right panel, that leads to large variations in the stellar to halo mass ratio. And so this is one particular observable, and we're thinking about other observables to forward model to constrain other parameters of this model observationally. So you may hear more about that sometime this week. Please ask me. But what I want to do in the remaining portion of my talk is describe this other project where I've been very curious to ask, can you use this model to tell you anything about how individual galaxies and their CGM co-evolve according to hydrodynamical simulations? And so for this project, I've been using the core Fire 2 zoom-in simulations as an initial test bed. And so whereas before we have to explore the parameter space and we're kind of doing it blindly, when we have simulations such as Fire, we can just go in and measure many of our free parameters, like the depletion time for the ISM, for example, to predict star formation rates as shown in the top left, the mass loading factor, the top middle, the wind specific energy, top right, and then metallicity terms for the wind as well as for halo accretion on the bottom. And so you can check these papers that we wrote a few years ago in 2020 and 2021 for more details on how we've actually extracted these parameters. I won't go into the details of that today in the interest of time, but I want to just show some results. So what we have now is we have the values of these free parameters. We have merger trees for individual halos from these simulations. We could run this model on those merger trees and we can ask how close do we get to Fire for individual halos, and do we get any new physical insights through this model? So the first thing that you might want to know about is the mass evolution. So here I'm showing predictions of our model versus measurements of the masses of the CGM, the ISM, and the stars from the Fire particle data for the 12 core Fire 2 halos. So in every panel, the solid lines are the measurements of these properties from the particle data, and the solid lines are our predictions from our model. And you can see that we're getting really remarkably close in terms of reproducing the evolution of individual galaxies as a function of time in terms of the CGM mass, the ISM mass, and the stellar mass. So the next thing that you might be wondering is, okay, we're showing the evolution of these baryonic properties, and I've also overplotted the total dark matter halo mass evolution. So what about the halo baryon fractions? So on the right here, I'm showing the average baryon fraction since redshift 2, which is roughly constant since then, in the Fire simulations, shown with the gray points, and then predicted by our model, shown with the magenta crosses. And you can see that in both our model and in Fire, there is this trend such that dwarfs have reduced baryon fractions. This has been known for, again, a long time, from, say, even the Fire 1 simulations, like by Fricke van der Voort. But with our model, we can actually provide an interpretation for this. So in our model, the dwarfs have reduced baryon fractions for two reasons. One, they're not accreting their full complement of the cosmic baryon fraction because their own galactic winds are reaching the halo radius and shock heating the gas, or assumed to shock heat the gas, to above the virial temperature, and therefore this preventative feedback reduces the accretion rate at RVIR below just FB times m dot times the halo growth rate. The second reason is that, as I said before, in these dwarfs, cooling cannot keep up with heating at some point, and so they have significantly overpressurized CGM, and so this leads to halo outflows. So they're ejecting previously accreted baryons. Now, just reproducing the mass evolution and the baryon fractions is not satisfying enough because you can get to the same mass in many different ways. And so you really have to look at the underlying gas flow cycles, the m dots that underlie SAMs and really what's going on in the simulations. And so it turns out that our model is also capable of reproducing the gas inflow and outflow rates. So this panel here I'm showing from left to right, the gas accretion rate at RVIR, the gas accretion rate into the ISM from the CGM, what I call m dot cool, then the galactic wind outflow rate, m dot wind, and then finally this halo outflow rate, m dot out halo. And just like before, the solid lines are the measurements of these quantities, these flow quantities from the particle data, and the dashed is our predictions from our model. And the halos are color-coded according to their redshift 0 halo mass as shown with the color bar. And you can see again that the dashed lines are roughly reproducing the solid lines over this huge range in halo mass and time. And just for completeness, we also reproduce the metal flow rates using a simple instantaneous single yield chemical evolution model as part of this. Okay, so it's all well and good to reproduce the masses and mass evolution and the mass flow rates, but what physical insights do we gain from this model? So it turns out that in our model, we predict that there is a phase transition from an early, cool, turbulent phase to a warm, hot, thermal pressure supported phase at late times, kind of similar in the vein of what Claude André showed just in the previous talk, but not as detailed. And so on this first plot on the bottom left, I'm showing just an example of one halo. I'm showing the different energy terms that we predict with our model and that we've measured in the fire simulations. And you can also check out papers by Jonathan Stern and Alex Gervich that have also measured CGM-related energetics as well as ISM scale-related energetics. And so this is a low-mass dwarf. And again, the solid lines are the measurements of E thermal and E kinetic, respectively in red and cyan from the particle data. And then the dashed lines are the predictions of our model. And you can see that in this low mass dwarf, which is representative of the other low mass dwarfs that we've modeled, this transition from an early cool turbulent phase to a thermal pressure dominated phase happens pretty early. So starting at, say, redshift 3 or so, redshift 2, age of 3 gigayears, the thermal energy dominates the energy budget for the CGM globally for these low mass dwarfs. For intermediate mass dwarfs or classical dwarfs, the transition happens much later. This is just because these halos, their temperature for the CGM is close to the peak of the cooling curve, and so they're able to balance the heating terms for longer. So they transition much later, but they do transition. And then finally, the Milky Way mass halos are somewhere in between. And in our model, the transition seems to happen more abruptly, as you can see with the red dashed line on the rightmost panel. But qualitatively, we're reproducing the significant rise in the thermal energy fraction for the CGM as a function of time as seen in the fire particle data. So one last thing I want to end with is you might be wondering, okay, so why exactly does the CGM undergo a phase transition? And the way that we thought about presenting this or really analyzing this is to look at the time evolution of the equilibria of our E-dot ODEs. So before I show a quick movie, I want to just say in words what we think is happening. So initially, cooling times are extremely short, densities are very high in the early universe, and so cooling is able to balance heating from dissipation of turbulence as well as from supernova wind energy input. However, as time goes on, the mean cosmic density is dropping, and the mean CGM density is correspondingly also dropping. And since cooling goes as n squared lambda, eventually at some point in our model, cooling cannot keep up with the various heating sources, and so the low temperature equilibria that the model lived at, they vanish. And so the model then quickly evolves to the remaining hotter equilibrium. So here is the movie just showing what I just said in words. There's the top panel here is the time evolution of the halo virial velocity in black, the turbulent velocity in cyan, and then the halo CGM sound speed, or equivalent of the temperature, on the right axis in red. And the dots mark where along the trajectory we are at the current time. And the bottom two panels are the really key ones. So these are E-dot thermal and E-dot kinetic versus the temperature and turbulent velocity respectively. And the black lines in these two bottom panels shows the total value of E-dot thermal and E-dot kinetic. And when these go to 0, that is an equilibrium, right? That's when E-dot thermal, E-dot kinetic goes to 0, that is the equilibrium value of T naught and V turb. And I want you to just focus on how those singularities evolve with time, and also focus on the dashed cyan line on the bottom left panel. That's basically the cooling curve. And you're going to see that march down with time, and eventually it can no longer keep up with the heating terms. So you see the cyan line at the bottom left panel is dropping. You have various equilibria appearing and disappearing. This is a bifurcation in the solution of the ODE system. And at some point, there's this critical point where there's just no more, cooling cannot keep up with heating. And so those two lower equilibria disappear, and you end up at this one last stable, hottest equilibrium. So I'm going to stop here. I can say a lot more about this and stuff that we're planning to do, but please be on the lookout for 2 papers early this fall by Chris Carr and then by myself on just presenting the model and its initial applications. And I'd love to talk to many of you throughout this week on further applications and extensions and so on and so forth of this model. And I'll stop there. Thank you. Take questions. Sandy.
Okay, thank you. So we have many questions. We will start here.
I'm looking for the second parameter in your theory, and wondering if you guys can predict a galaxy radius, because we see range and radii at a given mass, and that really seems to be the most important second parameter for properties.
Yes, I would love to do that.
Do you have any thoughts?
No, I mean, I think the first thing I would do is I can't, I mean, I would, I don't think I would try to predict the galaxy size. I would just use the simple assumption that the galaxy size is some fraction, whatever, 3% or so of the halo virial radius, and then from there, maybe try to model the ISM more self-consistently, which I've started thinking about. But yeah, I would love to talk more about that.
Yeah, thank you very much. Great stuff. So at the beginning, you said that these the density and temperature and these various parameters follow power laws, and then there's this overpressurization that your model allows for when the energy exceeds the binding energy. So I'm just curious, does that then talk back to these profiles? Because various simulations and even recent observations with the Sunyaev-Zeldovich effect have sort of support this idea of baryon lifting, out from the CGM beyond, well beyond a nominal virial radius or something. So I'm just curious, like, do these various parameters propagate back to the profile itself, and are there assumptions built into that might complicate these kinds of phenomena?
Yeah, that's a great question. Thank you for that. So yeah, the halo outflows only propagate back to the profiles in the sense of the normalizations. So the halo out when you're removing energy at the halo radius, it's a way to well, of course, to reduce the thermal energy. We assume that the halo winds have the same specific energy as the CGM, so it doesn't really, so I take it back, it does not change T naught. You could have it change T naught if you wanted it to by having the halo winds have a higher specific energy. We don't allow for that complication. The density normalization has changed because you're removing mass. In terms of changing the slopes of the profiles, I would love to do that, but then it just becomes a very complicated model where you have to solve for, the internal structural evolution of the CGM, and at that point I might just do like a 1D simulation or something. But I'd love to talk more about that if you have ideas.
We'll take our last question.
Very nice stuff. Is this working? Yeah.
Yeah.
So let me ask how you're determining the various free parameters in your model. For example, I noticed in the slide that you attributed to Carr's work that the energy loading factor is very low, like 0.1 or 0.2 for 10 to the 12 solar mass halos, and becomes much higher, like an order of magnitude or more higher, the lower mass halos. So what's the physics behind that? Do you understand it? And how are you actually determining it when you model a simulation?
So yeah, that's a great question. So for Chris Carr's work, we are just parametrizing A to M and A to E as power laws of the halo mass. And then we just fit, we're exploring the parameter space, the slope and the normalization to reproduce the Baruzzi relation. In fire, I can just go and measure it, and I've done that, as you know, and we published a wind paper last year for the fire simulations, the Fire 2 simulations. In terms of the physical causes, I mean, that gets into Claude André's talk for why we, why the fire simulations give us a particular A to M and A to E halo mass and retrodependence that they do. There's a couple different things that come into play. So there's, of course, the potential well depth of the halos. So lower mass halos, the winds can escape more easily, so maybe they retain more of their wind energy. There's a couple other parameters. So there's the level of inner CGM virialization that Claude Andre talked about. If your CGM is virializing the inner parts, the winds are going to hit a wall and they're just going to, thermalize and maybe not travel that far. There's also the burstiness level and how clustered your resulting supernovae are in the bursty phase or the non-bursty phase. And there's one other that we looked at in my wind paper and I can't remember anymore.
One way to discuss this is compare a well-known parameter, the mass loading factor, with your new parameter, the energy loading factor. They seem to behave in a somewhat similar way.
Yeah.
Here less for high mass halos, very much larger for low mass halos. Do they in fact work in parallel?
Yeah, they do. So yeah, eta M is high for lower mass halos and eta E is also close to 1 for lower mass halos.
Same phenomenon.
Yeah.
Moving the mass out and moving the energy out.
Yeah, exactly. Yep. All right,
Okay,
thank
so
you.
let's thank again the speaker. And then the next speaker is Nirmal Nerke that will talk about cold streams in high mass galaxies at high redshift.